right, let's get started. So final exam schedule is on the projector here. Okay, so final is going to be on Wednesday, December 13th at 10:30 a.m. 2-hour exam. Same place as last time, same seating location. So nothing has changed as far as location is concerned. Just please note the time. And we'll have next week to talk about the exam in more detail. So for now, just make sure you know the time and location, and then we'll have plenty to say next week about the exam. Okay, so today we're going to look at section 5.5, today and Friday. We're going to split this section into 2 parts. The topic of 5.5 is integration by substitution. So what this is actually the chain rule in reverse. This is what happens when you receive a derivative of something that you had to use chain rule to get, and you want to undo that layer of chain rule to get back to the original function. And so, for example, let's look at this function right here. One-fourth times x squared plus 3 to the 4th. We know how to take the derivative of that by the chain rule. Right? So it's 1/4 times 4, x squared plus 3, reduce the power by 1, and then multiply by the derivative of that, 2x. And so at the end, if you clean this up a little bit, we get 2x times x squared plus 3 to the power of 3. So we had to use chain rule to get to this part. Now, if you didn't know where this thing came from, and you're given this thing, and you're asked to integrate that, you need to get back to here, but how would you do that? So if we didn't know f of x, how would we calculate this? How would we integrate that thing? Okay, knowing where it came from, this seems pretty obvious, but you can see if you're given just this thing right here, it's quite complicated. We could multiply this out 3 times, but that's a lot of work. There must be an easier way to do this. So this is how integration by substitution works. This is the problem we're investigating. We're going to make one substitution in this integral here. I'm going to call this part right here, x squared plus 3. I'll call that thing u. And why did I choose that? I'll talk more about why we choose that to be u and how you can tell in general what you want u to be. But for now, I want to show you the processing, how this works. And then we'll focus on what u should be in when we look at different examples. Okay, so I made a choice to let u be this thing here. then we're going to find the differential of u. We did that back when we did the linear approximation. It's just derivative du equal to derivative on the right-hand side times dx. Okay, so I got my u and I got my du. Now, when I take this thing here, rearrange this just a little bit. Everything inside the integral is multiplied, so the order is irrelevant. I can move things around any way I want. So I'm going to choose to write x squared plus 3 cubed here, and then grouping together 2x and dx into some other group. Now the reason is because if you look back to what we called u, x squared plus 3 is u. So this group right here, that's simply u cubed, right? This guy is u. It's got a power of 3, so that's u to the power of 3. And whatever's left in here is du. And therefore, the original integral now all of a sudden looks vastly simpler. It's u cubed du, right? And you treat that in exactly the same way you would treat x cubed dx. All we did here is a change of variable. U cubed du, integral of u cubed du, and the integral of x cubed dx are the same thing fundamentally. The only thing different is the variable. So we know we're going to get 1/4 u to the 4th plus c. And after we've done the integration, now we'll undo the substitution we did earlier. Square here, sorry. Right? The middle of last page, we said u was x squared plus 3. Now I undo that. And so I end up getting 1/4 u to the 4th plus c. Okay, and that's what we started with. We started with the function 1/4 x squared plus 3 to the power of 4th. The plus c, of course, means there could have been a constant that disappeared during the differentiation. But in the end, we ended up getting the most general antiderivative that matches what we started with. Okay? Now, does that process make sense? Is it clear? Okay, so now you see, once you have the u, you've made a choice to be u, or you're told what u should be, then everything that follows is not terribly difficult. The key part about all of this is in choosing the correct u. And I'll show you a few different examples with different kinds of functions. And you'll see how we can choose u. Let's look at this one. The indefinite integral of x squared times the square root of x cubed plus 4. So some mysterious function has this as a derivative. We want to find out what that function is. Okay, the first step, all I'm going to do is rewrite our root as a power. That's all I'm going to do. The basic idea behind choosing u is you look at the integrand, the stuff you're integrating, that's called the integrand. Choose the part of the integrand whose derivative is a multiple of the other part. You'll see, you'll see. And I'll give you another rule of thumb that in general, if you lose track of what to do, there's a rule of thumb that you can follow. But let's be more precise, a constant multiple. So what do I mean by this? If you look at the two parts of the things we're investigating, there's x squared. And for the moment, I'm going to temporarily set aside that power 1/2 and just look at x cubed plus 4. And if I look at the x cubed plus 4, the derivative of x cubed plus 4 is 3x squared, right? And it is 3 times the other part. So that's what we mean by the constant multiple of the other part, which is a constant multiple of x squared, right? So I got x squared and x cubed plus 4. If I take the derivative of one of them, if it turns into some constant multiple of the other part, then that's what I want u to be. Okay? And that's how you choose u in general. You have to analyze what's going on inside the stuff you're integrating. Try to find two parts that are related by one derivative. There's a rule of thumb that you can follow often, but not always. You will want u to be the part with higher power. Or the part that's more complicated. It's the rule of thumb that you can follow, but there are exceptions to that. We'll see that on Friday. For now, today we'll focus on the simpler cases. Friday we'll look at some slightly complicated cases. But that's a pretty good rule of thumb to find. If you break things into two parts, choose the part with a higher power or the part that looks more complicated. In any case, once you've decided what U has to be, the rest of the steps are just the same as last example. Okay? All right, so let's work out this part, this problem right here, with that choice of U. I'm just going to rewrite the problem here. We made the decision to let U be x cubed plus 4. Now, next step, if you look back at the first example we did today, we find the differential of U. So du is derivative of that, 3x squared times dx. Then we sub these into the integral. And at the end, we want to get rid of every reference to x. Anything containing x, anything containing dx, they all have to go. We want these guys to go in there in place of x and dx. Rearrange a little bit if it helps. The first part of the substitution should be pretty obvious. Once you made a choice of what U should be, you can immediately pick out the part that has U, right? So this guy here, U to the power of 1/2. This group is simply U to the power of 1/2. Now, if you look at this part right here, whatever's remaining has to be related to du in some way. Du is equal to 3x squared dx, but I only have x squared dx. So if I divide out that 3, then I see what I have here is related to du, but not precisely 1 du, but actually 1/3 of a du. So this guy here is 1/3 times du. Any question on how we got that 1/3 du? Okay, is it clear to everyone? Okay, then let's proceed. So now notice all the x's and dx are gone. So this is simply 1/3 times u to the power of 1/2 du. And now it becomes very simple. That's the whole point of integration by substitution. Take a complicated looking thing, change it into something simple with a different variable. So let's see, 1/3 doesn't do anything. It's a constant multiple. U to the 1/2, just basic power rule. Add 1 to the old power divided by the new power plus some constant. So that's equal to 1/3 times the reciprocal of 3/2, u to the 3/2 plus constant. So 2/9. The last step here, we get u back out. We're done with u. u to the 3/2 is the same as u to the 3/2 plus c. And of course, you can always check, right? It's a very, very simple thing to check. Let's take the derivative of what we just got. We better get x squared times x cubed plus 4 to the 1/2. So let's see, we get 2 over 9 times 3 over 2 x cubed plus 4 to the 1/2 times 3x squared. And so we get 1 over 3, 3 go away, so this is x squared times x cubed plus 4 to the 1/2. And it matches the thing you were integrating in the first place, so therefore you know this must be the right answer. Any question on this example? Good? All right. Let's look at the next example. Like I said earlier, and as you can see, if you have the u, make the right choice of what u should be, what you have to do usually is not terribly difficult. Let's look at this one. Dx over 1 minus x. Okay, this is just a little bit of a more compact way to write 1 over 1 minus x times dx. So one way we can proceed is to think of this as the integral of the number 1 times 1 minus x to the minus 1 as a power. And just like in the last example, we're going to look at these two parts here. Again, like the last example, notice we've momentarily just kind of ignored that power to the 1 minus 1. We're looking at the root of that function right here, 1 minus x versus 1. So those are the two parts we're comparing. And what's the derivative of that? It's pretty complicated, right? Is that a constant multiple of the number 1? It's not, right? Now, if I ignore that power to the minus 1, then when I take the derivative of this, I get minus 1, which is directly related to some multiple of that. So that's the reason why we temporarily shove that power aside. It doesn't help us in getting the right u. So the two green parts, the two parts in the green boxes, just like we saw in the last example, derivative of 1 minus x is minus 1. And that's, of course, a constant multiple of the number 1, right? It is also the more complicated part. You got these two parts. One is simple. 1 minus x is more complicated than that. So either way you look at this thing here, it will tell you that you want u to be 1 minus x. So we want u to be y minus x. Okay, any question with that part, with how we chose that u? Good? Good. Okay, now we got u. Then we find the differential, du. Derivative of this minus 1 times dx. Bring this back down here. Look at things. We get 1 minus x to the minus 1, 1 times dx. Just like before, you can spot what u is going to be because you know what u is. So that's u to the power of minus 1. What about 1 dx? What does that turn into? Right. If I have a minus here and then I get du, but I don't. So from here, you can adjust that by seeing that du minus du is equal to dx. 1 dx, of course, right? That's what I got. That's what I would like to have. This is what I have. So you can adjust this by multiplying and dividing constants. So that's negative du. And that turns into minus 1 times u to the minus 1 du. When you integrate that, the minus 1 doesn't really do anything. And what's the integral of u to the minus 1? Good, very good. ln of the absolute value of u. Then we add some constant. And after you've done the integration, now you get rid of u. You're done with u. U has served its purpose. We get rid of it. And there we go. Okay? Of course, you can always take the derivative of this to make sure you do get 1 over 1 minus x. Just by looking at it, we can see pretty quickly that we get the right thing. 1 over 1 minus x times minus 1 with another minus 1 makes that a positive. So that looks like the right one. Questions on this example? Good? Okay. All right. Let's check out this next one. In fact, let me give you 3 minutes to try this on your own. Use the same principles we've applied in the last examples. These are not polynomials anymore, but the principles stay the same. Choose u that's related to the derivative of some other part, and then go through the process. Okay, so take 3 minutes to give this a shot. Okay, that's 3 minutes. Let's start. What would be an appropriate choice of u? Sine of x. Is that the only choice? Could I have used u as cosine of x? In fact, yes. And we'll work through both of these. In this problem, there are two possible choices of u. And the reason is because sine of x and cosine of x are directly related to derivative of the other. The most obvious choice, the most natural choice probably would be u equal to sine of x, because then du is cosine of dx, cosine of x dx. But there's nothing wrong with the other choice. We'll work through both of them. So the first one, if we let u be sine of x, then the differential is cosine of x dx. And you can see there's really nothing I need to do to the original integral here. Everything is already set. That's u. And cosine dx, that's du, directly substituted out. So that's 1/2 u squared plus c, or 1/2 of u squared plus c. Right? And I can always check that I did that correctly by taking the derivative of whatever I just got. So I get 1/2 times 2 times sine times cosine, right? Chain rule. Bring the 2 down, reduce power by 1. Derivative of that thing, cosine. So I get sine cosine, which matches what I integrated. So therefore, I must have gotten this correct. That's the right answer. And there's nothing wrong with choosing u to be cosine of x. We'll work through that one also. This time we'll let u be cosine of x. So du is equal to negative sine of x dx. If you use that choice of u, then the integral we're trying to solve is just a little bit more complicated, not by a whole lot. That's u, of course, right? And if I have a minus sign here, then that's du, but I don't. So I can multiply by -1, like we did with the last example. Then I get negative du. Then we integrate negative u du, and we get -1/2 u squared plus c. This time u is cosine plus c. Right? Now, this one doesn't look like what we just got. But as long as I get the same thing, I know that's also correct. So let's check that. You got to remember that trig functions, every trig function can take on an infinitely many different forms. With all these identities we have available, the same function can have many different kind of appearances. So let's see. We get minus 1/2 times 2 times cosine of x. By the chain rule, we need a negative sign. And minus 1/2, 2, and minus 1, these turn into just a 1. So we get cosine times sine, which also matches that. So this is also correct. That's the danger, with not really danger, but the problem, not really a problem, but a feature of trig functions. They can look different, still being the same function. Okay? How many people got this one right? Okay, how many of you went with the first choice of u that we did? How many of you went with the second choice? Okay, good, good, wonderful. Any question on this example? Yeah. We would not write a question that has that kind of ambiguity. Okay. We're aware that this can happen, and we won't let that. We'll find a way to make this unambiguous. So we might give you a function, a point that the function passes through. In that case, you can find c. We might ask you what the function will be at some certain value of x. In that case, whatever form you get a, if once you plug in a value of x, you get a number instead of a function. So we have ways to make sure that this doesn't happen on the test. Okay, other questions on this example? Yeah. With WebAssign, my understanding is that it is smart enough to know that this and that are the same thing. Okay, that this thing I boxed and the 1/2 sine square of x are the same thing. Generally, that's true, but there are some problems that can be a little bit more picky than others. I'm sure you're aware of that, but generally, it is smart enough to understand that trig functions can have different looks. So I wouldn't worry too much about that. Okay, let's look at a couple more examples. Let's look at this one involving natural log. Natural log of x squared over x dx. Okay, so again, some function gave us this as a derivative. We're trying to recover what the original function might have been. When you're just starting out, it helps to break things apart and write them as a product, and then go through the way we check things. I know x squared is not related to the derivative. X squared has not a derivative that's related to 1 over x. So I want to include the natural log of x in a comparison I'm going to make. The derivative of natural log of x squared is 1 over x squared times 2x. Derivative of natural log of something is 1 over that something times the derivative of that something by the chain rule. So that's equal to 2 over x, or 2 times 1 over x. And so that this tells us that we will want u to be ln of x squared, because its derivative is related to a constant, is equal to a constant multiple of the other part, right? So we want u to be ln of x squared. And that's the hardest part. Once you made that choice, everything else is a consequence of that choice you made. du is 1 over x squared, and we did that over here. Okay, so this thing we're trying to integrate, ln of x squared is obviously u. And if I have a 2 with a 1 over x dx, and I get du, but I don't have that 2, right? So this tells me that 1 over x dx, which is what I got. I want this, but I got that. So I divide it out. So we see 1 over x dx is 1/2 times du. And all of a sudden, that integral involving natural log and all that stuff turns into just a simple one, 1/2 u du, which is 1/2 times u squared over 2 plus a constant, or 1 over 4 u squared plus a constant. And as usual, now we've done the integration. We don't need u anymore. We get rid of u. We go back to x. Okay, so there's the thing that gave us this as a derivative. Generally, if you see natural log in the thing you're trying to integrate, that is generally the choice, what you want u to be. So I'll write that down too. Often, but not always, ln of something is a good choice of u. Okay, those are rules of thumb that often work, but not always. There are always exceptions to a lot of these rules. Let's do one more. Let's do one involving e to the x. E to the x over 1 minus e to the x. And again, rewrite these in terms of products. It can help you identify u. If I look at these two things here, I know the derivative of 1 minus e to the x is simply minus e to the x, which is what we got here. But the derivative of e to the x doesn't have that 1. And if I include this minus 1, then I get a complicated derivative that's not a constant multiple of e to the x. So we don't want to include that minus 1 here. It'll make the derivative of that part very, very complicated, and that's not going to help us match things. And looking at these two here, we know derivative of 1 minus e to the x is minus e to the x, which is minus 1 times that. Right? That's what I got. So a good choice of u would be 1 minus e to the x, which, by the way, again, is the more complicated of the two parts. It's another case where the rule of thumb actually works. It's a pretty useful one to go by until you run into exceptions, and then it doesn't work. But anyway, either way you look at it, now we know what u has to be. Then everything else is a consequence of that. So we just go through that. E to the x dx is du, and minus e to the x dx is du. I don't have a minus, so I'll just multiply it to the other side. Sorry. Du, there we go. Times minus du. So that's the same as integral of negative u to the minus 1 du. That's the negative of the natural log of u plus a constant. And as usual, once we're done with u, we get rid of it. And there we go. And of course, you can always make sure this is right by taking the derivative to match this. If it doesn't match, something is wrong. Possibly the choice of u. Another common mistake that can happen is in this step right here. You always have to adjust the du equation by a constant somehow. Check that step. All right, that's it. See you again Friday.